Hello, everyone. Welcome to this week's lecture for the MTV Nuclear Engineering Summer School. Just a quick reminder, please feel free to put any questions into the Q&A section. We'll go over them at the end. If we don't make it to your question by the end of this lecture, please feel free to reach out to us and we'll respond to you and answer your question. And today's lecture will be given by Erin Neely, who is an incoming third-year PhD student in Professor Potsy's group. She'll be discussing today about organic glass fabrication, which is also the focus of her research. So, Erin, take it away.
Yes, thank you, Sander. Hello, everyone. As he said, my name is Erin Neely, and I'll be presenting today for MTV Nuclear Engineering Summer School on organic glass synthesis and characterization. I hope that everyone can hear me okay. Please let the moderators know if you're having trouble.
Coming through great, Erin.
Yes, thank you. First, just to give you a quick outline of what I'll be talking about today. First, we're going to do a little introduction and overview of organic glass scintillators, or OGS, including our melt casting process at the University of Michigan. Perhaps a more general overview of organic scintillators and properties and characterization, and how we improve our OGS synthesis by melt blending and incorporating dopants. And then how do we use it in real world applications? And then we'll just wrap up and show you some reference material. So let's begin. First, a little bit of a brief introduction and motivation. If you guys have been in the summer school, you probably know by now that radiation can be detected and quantified with various types of scintillators, in which incident radiation excites the matrix material and then it de-excites as visible light. Organic scintillators specifically are used in non-proliferation, medical, and physics applications. Organic glass scintillators in particular are a newly developed material with high light yield, competitive resolution, and the ability to be remelted and reconstituted. You can see a couple of pictures of organic glass scintillators over there on the right, with the hollow cylinders fluorescing under a black light, visually showing the scintillation properties. Now, just to talk a little bit about why we like organic glass, it is true that organic scintillators in general have worse gamma ray efficiency than inorganic because they're not sensitive to full photoelectric deposition, only the Compton effect, but they do have superior timing properties and can be sensitive to multiple particles, meaning gammas and neutrons and betas. In general, our best performing organics include transstilbene. However, this is a crystal which requires a complicated growth process that limits the scintillator volume and is not on the market anymore. Organic glass scintillators, on the other hand, are an amorphous solid and are much easier to cast by just melting it down and cooling it. That means it is very scalable, reusable, amenable to additives. It's pretty straightforward to just mix the additives into the melts. Therefore, they can be loaded with isotopes to give them more sensitivities, which I'll be talking about later. They can be melt cast into unique geometries for various applications, and it is almost as high performing as stilbene. It's about on par with crystals, which are better than liquids, which are better than plastics. We don't really like using plastics unless we have to. For a little bit more background about OGS, the material was originally developed by Sandia National Laboratories, or SNL for short. It is a 90-10 mixture of a primary fluorophore P2. It has a really long chemical name, but it's really long, so we just call it P2 for short, with a bit of a molecular stabilizer, PB3, and a tiny amount of the secondary fluorophore, bis MSV, as a wavelength shifter. This wavelength shifter shifts the emissions even further into the blue visible light spectrum. And the organic structure of the primary fluorophore is sensitive to both neutrons and gamma rays. Over there, you can see on the right a plot of the pulse signals up on the top right and some cubes on the bottom. Now, what do we mean when we talk about glass? Well, there are actually multiple types of glasses. It's a state of matter, not a material. Examples of inorganic glasses include silicate-based oxides, so your window glass, and even metallic glasses. Among organic glasses, thermoplastic or glassy polymers are the most common, but they're not ideal for scintillation because they have alkyl chains which are covalently bonded and get entangled. Molecular glasses, on the other hand, or monomeric glasses, are comprised of individual small molecules that are held together by van der Waals forces. They have no long polymer chains, but instead they are made of individual molecules, so they don't preferentially scatter light in any particular direction. They do not follow the long-range order of crystals either. Sort of a critical concept to talk about here is the glass transition temperature, or TG. So a glass is actually similar to a liquid that has been supercooled below its solidification point, except instead of the molecules crystallizing in an orderly fashion, they remain in an amorphous or disordered fashion and approach the solid state, but the glass has a greater molar volume at the same temperature than a crystal. A little bit of history on organic glass scintillators. They were actually first reported in 1958 by Downs and Smith. These had about 60% of the efficiency of anthracene, which besides stilbene is another common reference organic. However, unfortunately, after 4 hours at room temperature, they would fully recrystallize and become opaque, which is bad. We want it to be transparent and optically uniform. So these ended up not being pursued because additives in PVT and PS were working just fine. There was a need to stabilize this glassy phase, which was more recently worked out. So we know that molecular size has an impact on stability. There is a critical radius of the crystal above which crystallization occurs spontaneously, yet below which it stays as a glass. And the more free volume there is, the more likely it is to recrystallize or pack together to minimize that volume. Adding a stabilizer like PB3 lowers 2P2, lowers the concentration of both, which makes the recrystallization of either less likely. There is a formula for the recrystallization rate, R equals N sub S times e to the minus delta G over KBT, all times ZF. NS is the number of nucleation sites, which of course is going to depend on the free volume. E to the minus delta G over KBT is a thermodynamic factor, which represents the probability that a nucleus of the critical size will grow at the nucleation site. And ZF is sort of a fudge factor related to viscosity and diffusion. So in designing glasses, we need to have high stability and good scintillation properties. Transparency is the key, especially in bulk materials. We also care about exciton transport. This is directly related to transparency, as the scintillation light is related to electron yield and electron hole transport. We need to have good mechanical as well as optical properties. Glass is kind of fragile, but there are things we can do, like melt blending with polymers, to improve that. We like the compositional variability, which means we can incorporate additives We like that all the molecules are identical in this monomeric glass because pulse-shape discrimination between gammas and neutrons, which I'll talk about in a bit, is particularly sensitive to impurities, disorder, etc. Now we're going to talk a bit about how we actually melt cast the glass at U of M so we can use it. Picture number 1, you can see bulk OGS in a vial. In the second picture is actually a video of the bulk OGS being melted down and attached to a vacuum, which is above the top of the video, but you can see the air bubbles kind of coming out under the heat gun. And then once it's all good and degassed, we pour it into custom silicone molds and let it cool gradually in the oven for 14 hours. Recently, we've also been experimenting with a procedure using a vacuum oven the whole time. Once the glass cools and we pop it out of the molds, we put a protective PVA coating on it to prevent recrystallization and wrap it in Teflon tape as a diffuse reflector to minimize light loss. Just to show off some of our equipment, it's pretty simple, really. We've got a hot plate, a rough vacuum, a scientific oven, mold kit. You can see an example of a cast mold over there on the bottom right, which we would pour the glass in. And we use the mold negatives in the mold making tray to model the shapes that we want. Now, after the glass comes out, you can see that it still has some bubbles and peeling in these pictures over here on the right. That is why we need to degas to prevent air bubbles in the glassy state. That also removes oxygen, which can cause yellowing in the long term. And the higher density it is, with the fewer nucleation sites, which an air bubble would be, the less likely it is to recrystallize. We cool it over 14 hours because that will prevent stress, cracking, and instability once it cools. The PVA coatings also prevent nucleation sites and recrystallization on the surface via mobile dangling bonds. This is especially important because we need to use silicone optical grease to couple it to the PMT for testing. If we don't have a PVA coating, it's going to recrystallize fast. I've learned that the hard way. To verify the reproducibility of our melt casting, the group did some experiments a while ago with casting 15 6mm edge OGS cubes in 3 different batches to investigate the variations in performance both within and between the melt casts, and the batch averages are within statistical error pretty much. So our melt casting process is reproducible. Now, once we have cast the glass, how do we characterize it? This is also where I'll be getting into some of the properties of organic scintillators in general to help us understand better what exactly we want to characterize with the glass. Organic scintillators in general have a couple of different types of interactions. They are sensitive to both neutrons and gamma rays. A gamma ray will Compton scatter off of an organic material. So we need to know the Compton scattering equation for it to understand what is going on and read our energy output. Whereas neutrons would elastically scatter off a proton or less frequently a carbon nucleus. And this requires more extensive characterization like time of flight experiments to relate light outputs to energy. Without doing these, we can't quote light output in energy directly. We have to quote it in electron equivalent or MeVEE. There are other interactions that can happen in scintillators, but these aren't really feasible with organics because they're not high enough in Z value. The probability of photoelectric absorption is very low because the electron cloud is much less dense in those low Z elements. The probability you can see is proportional to z to the n between 4 and 5 over the energy of the gamma to the 3.5. So basically, with the energies we're working in, we're not going to get it in our low Z inorganic scintillators. Now, this is a bit unfortunate because spectroscopy typically uses photopeaks to identify isotopes. But in organics, we can use a Compton edge to identify the energies of the incoming gamma rays. And there is a formula for where the Compton edge should be based on the photopeak energy. A bit of a visual diagram of Compton scattering. You can see the incoming photon strikes an electron. The electron recoils and the photon scatters following the laws of conservation of energy and momentum. So you end up with a partial deposition of energy from the photon to the electron. Whereas in the photoelectric effect, the photon would be incoming, hit the electron, eject it, but there's no recoil since the incoming photon has deposited all of its energy. To see what it looks like on a spectrum, you can see on the top right, there's a spectrum from an inorganic detector. You have the X-ray photopeak from the electronic interactions within the shells. There is a backscatter peak from Compton interactions and scattered photons creating further interactions. There is a Compton shelf, and this is what I'm talking about with the Compton edge being at a specific energy that is related to the gamma photopeak. At cesium-137, which is kind of our gold standard because it's pretty much monoenergetic, the gamma photopeak is at 662 keV. So per the formula, we know the Compton edge has to be at 478 keVe. And the Compton edge is a little bit tougher to identify on a plot than the photopeak, but with the right code, you can do it. This is the equation for Compton scattering. 1 over E prime minus 1 over E equals 1 over MEC squared, 1 minus cosine theta. You can solve that for a head-on collision to get E prime. The maximum transferred energy would be 2E squared over ME, or mass of the electron, times C squared plus 2E, where E is the original energy of the photon, and then the backscatter peak would be whatever is left over from that. Important scintillator characteristics include light output, which is kind of what I was talking about before. How many photons or how much pulse do you get? You can find the amplitudes or the integrals of the pulses to measure this, but basically how much light do you get how much output light do you get per incident photon? To get an apples to apples comparison, you can measure the same source on the same system and see which scintillator produces more photons. That will also help you with new scintillators because you can compare to known values. On the bottom right, you can see a plot of light output in MeVEE versus the recoil proton on energy for, I imagine this is neutrons detected on still beam versus organic glass. And you can see that the organic glass is actually doing a bit better in terms of light output. So that's great news for us. We also care about energy resolution, meaning how precise is the scintillator in terms of what energies it's identifying. We typically derive this from the full width at half max of the photopeak derived by the centroid and report it in a percent value. However, for organic scintillators, which don't have a photopeak, this is a little bit more complex, and we can do Compton coincidence experiments, which I'll bring up in a little bit. We can directly look at coincidence timing resolution in separate experiments, or CTR. We care about when the pulse starts to rise and how long it takes to decay. and therefore we can determine how fast the scintillator is responding after it is hit with the incident radiation. And many of these also have pulse shape discrimination or PSD capabilities between gamma and neutrons. Just to go into a little bit more detail about recoil proton light output, in order to convert the light output from a neutron pulse to an incident to an energy function, we need to know the exact neutron energy for different light outputs. We can do this with the time of flight of the neutrons. We set up a trigger detector right next to the neutron emitter to essentially start the clock, which you can see in the picture, the trigger detector over on the far right next to the californium-252 source. And then once the trigger detector is started by a spontaneous fission, we measure the amount of time it takes for another neutron to stop in the organic glass detector. And then we subtract the start time from the stop time to measure how long the neutron took to fly. And with our handy dandy physics equations, which are not linear, but we can still work with them, we can then convert to neutron energies that the detector is getting. To tell you a little bit more about Compton coincidences, we can measure a gamma ray emitter such as cesium-137 with an inorganic and an organic detector in coincidence to convert those Compton counts to counts where we can see the energy resolution a bit more clearly. We're interested in gamma rays Compton scattering from the organic and then being absorbed photoelectrically in the inorganic. We time correlate and energy gate our data based on the backscatter peak in the sodium iodide and then compute the energy resolution from there using the usual formula for the photo peak, full width half max of the peak over centroid times 100%. Share some data on energy resolution from both OGS and Stillbeam. Our group used the cesium-137 Compton coincidence technique with both organic and inorganic sodium iodide detectors to determine the effective energy resolution of the organics at 662 keV. We had a couple of different cubes in a specific setup. We tested, I won't bore you with the details on that, but specular reflection, active wrapping, as opposed to diffuse, does improve the energy resolution a little bit. And our OGS is actually better than Stillbeam. These are some over here on the right, you can see some adjusted plots for each setup, and you can see the energy deposition peak with some background subtraction projected. This was before my time, so I don't know everything about it, but this is how my understanding goes. I have directly done work on coincidence timing resolution. We can find the total system resolution with these experiments. We have two identical, or as identical as we can get them, detectors facing one another with a positron emitting source, usually sodium-22, exactly at the midpoint. This has a beta plus or positron decay, so it will emit two annihilation photons going in exactly opposite directions. And if the two identical detectors are the same distance apart, then it should take exactly the same time for the photons to arrive. So we can use the difference in the measured pulse times to determine the time offset of the two scintillators relative to one another. We fit a histogram to the time differences of coincidence events and find the centroid. Just to illustrate some coincidence time resolution with OGS and Stillbean, here is what we did with a couple of 1-inch diameter cylinders. So all of that, well, except for the time of flight, was talking about detection of gamma rays, and the time of flight was for talking about detection of neutrons. Now, how can we tell the difference between gammas and neutrons and when we get them? That's where pulse shape discrimination, or PSD, comes in. It refers to a detector's ability to distinguish different types of radiation, usually, as I said, neutrons and gamma rays. The neutrons elastically scatter off of heavier protons, which have more ionization density and thus can create a higher density of triplet states. And when these annihilate, we get delayed fluorescence. In picture B on the bottom, there's a little diagram of energy transition states. And then over to the right of that picture, you can see a further diagram of direct excitation and emission from between singlet states versus excitation to the triplet state, migration via triplet annihilation, combination to a higher singlet state, relaxation, and then delayed fluorescence. This comes out in the shape of the pulses, normalized amplitude versus the digitizer sample number. You can see in this picture on the top left, there are two pulses. Neutrons are blue, as always. Photons are a reddish orange. And you can see that the neutron pulse has a bit larger tail region for the same pulse amplitude. So we do pulse shape discrimination by taking the tail integral and dividing by the total integral, because that should be greater for neutrons than it is for gammas, whose main mode is prompt fluorescence from singlet states, because they scatter off of lighter electrons, which deposit their energy over a longer range. And then when we take all of those pulses together and make a two-dimensional histogram of those tail to total integral ratios versus the total pulse integrals as a proxy for energy, you can see two distinct bands of neutrons and photons. Notice that the neutrons have a higher tail to total integral ratio, and we draw a line of discrimination between the bands. In OGS, as in other scintillators, we quantify this PSD capability with a figure of merit, or FOM. The left-hand picture, you can see a bit of an illustration of the FOM. We make a histogram of all the tail to total integral ratios, and there should be two distinctive peaks, a lower one for the gamma and a lower value one for the gammas, and a higher value one for the neutrons. And then we take S, which is the distance between the centroids of the two peaks, and divide it by the sum of the full width half maxima of both, and that's our figure of merit. Our group also tested some bare diffuse wrapped and specular wrapped OGS slabs for their figure of merit values. The specular was the best, probably because of less light loss and greater overall yield, but even the diffuse wrapping was better than not having one at all. To talk a little bit about OGS properties as compared to other materials, it is comparable to trans-Stillbean crystals and superior to traditional plastics, with an even faster decay time. The relative cesium-137 light gamma ray light yield, which is set at a reference value of 1.00 for trans-Stillbean, you can see is greater than 1 for P2 based OGS, whereas it is less than 1 for the plastics. It does not have its PSD figure of merit is not quite as good as steel beam, but still significantly better than the plastic, and its decay time is even lower. But that's not all. We can also melt blend OGS with other things to get more of the properties we want, which is what I am directly researching. Some additives we use to alter the mechanical properties of OGS because specific applications may require more mechanically robust scintillators. We don't want to take our big fancy detector out in the field and then just have it break, right? OGS on its own is very brittle, so that is a serious concern. We have hard and soft approaches to altering the mechanical properties. The hard approach would be just melt blending with polymers to increase the strength. Specifically, these would be polystyrene, polyvinyl toluene, and or polycarbonate, which give different results. There is also a soft approach of adding a plasticizer to increase the fracture toughness and plasticity of OGS. A little bit of a chart about how the melt blending process works. It's really very simple. You grind up the glass, grind up the plastic, melt it all together, and pour. Sandia's investigation found that polystyrene that polystyrene was the best thing to melt blend with P2. The P2 does need to be only around 60% by weight, because if it gets much above that, there can be phase separation between the P2 and the polystyrene. Some more illustration of the styrene monomer becoming the polystyrene polymer. That chemical structure is physically mixed with the compound P2 and a bit of bis MSB. You can see the finished cylinders on the bottom. More recently, we've also been investigating metal loading in organic glass scintillators. Incorporating metals into OGS increases their gamma ray sensitivity. Specifically, our group has been working with RMD on a tin-loaded organic glass mixture. The organotin is melted down with OGS at RMD, and then the organotin is mixed with OGS at RMD, mechanically mixed together, and then we melt all of that down and melt cast it right here at on top of the melt casting that RMD does, which you can see in the picture on the top. The organotin compounds have demonstrated some promising results. Most importantly, because of the metal loading, photo peaks are now observable in organic detectors where they weren't before, and it doesn't really compromise fast decay and PSD capabilities. Some of RMD's results are in the picture on the bottom. In the picture on the left, the OGS is blended with a polymer and the peaks are not well resolved, whereas in the picture on the bottom right, the 60 keV peak from americium 241 is well resolved in the tin-loaded glass. These are some plots that I made based on my own research with the tin-loaded organic glass. Over on the left, you can see 4 12mm cubes, two regular, 2 tin-loaded, and one of each of those cast in our clear Silgard 184 mold or our blue Mold Star mold. You can see that the light yield or location of the Compton edge is a bit depressed with the tin-loaded glass, but you can see a photo peak to the right of it, whereas with the regular glass, it's just noise. And when I investigated the PSD figure of merit of the tin-loaded glass as compared to regular organic glass and a still beam for comparison, it is not quite as good for the tin-loaded organic glass as it is for the regular glass, maybe because of that depressed light yield, but PSD is definitely still possible for energies in the hundreds of keVEE range. We can also achieve triple PSD in the organic glass if isotopes with high cross sections for thermal neutrons are incorporated, specifically boron 10 and or lithium 6. This will give you a thermal neutron island on the heat map of tail to total integral ratio versus relative light yield or incident energies, which you can see right here. These are the thermal neutrons that are being detected in capture cross section. Nguyen and his colleagues used TDB, which is an aromatic molecule with boron incorporated, fairly easy to synthesize at 20% by weight in OGS. And the boron compound also acts as a plasticizer to make the OGS a little bit less brittle, so it's a win-win. Now, ultimately, why are we doing all of this? It's great that our OGS is doing so well, but what do we want to use it for? Well, some specific applications of OGS would include radio xenon monitoring, which as a nuclear security group, POTSI's DNNG group pays a lot of attention to. Radioactive isotopes of xenon are a key indicator of nuclear weapon detonation. They can be detected with beta-gamma coincidence detection systems that use plastic scintillators, but as I've mentioned, plastic scintillators are not as good as the organic glass, and they can exhibit a radio xenon memory effect, causing them to get false signals after trying to use them second or subsequent times. Still being is expensive and difficult to shape. So we want a new scintillating material with high performance, good shaping capabilities, and no memory effect of interest, which is where organic glass comes in. You can see a diagram of one of those monitoring cells over a global map of the International Monitoring System for Unauthorized Nuclear Explosions. Characterization of the radioisotopes in the environment provides, well, characterization of the scintillator provides valuable insight into its potential in radio xenon monitoring. Compared to plastic scintillators, we do ideally want better energy resolution, better timing resolution, better PSD, and lower memory effect, just better performance all around, basically. Here are some illustrations of the background knowledge we would use to monitor radio xenon. On the top left is a plot log scale with xenon 135 over xenon 133 activity on the y-axis, xenon 133m over xenon 131m activity ratio on the x-axis. And there is a clear dividing line between outputs from nuclear power plants versus nuclear explosions, depending on the relative activities of these isotopes. Below is also illustrated the beta on the x-axis and gamma on the y-axis depositions of the different isotopes as a model of what we would be looking for with the organic glass. The beta cell itself would need to be an organic scintillator because they're much more efficient for low energy beta particles, yet it would also contain the gas sample being measured. These usually have a domed shape to improve their structural integrity and redirect the signal back into the readout. They also need to be thin enough to allow gamma rays to escape into the surrounding inorganic gamma cell, usually a sodium iodide, yet thick enough to still detect betas and maintain their structural integrity under vacuum. On the top right, you can see a picture of the beta cell approximately to scale, and on the bottom right is just a chart of the various modes of decay of radioxenon that would be looking at. We are looking into 3D printing these beta cell molds so that they would dissolve out of PVA, so that they would dissolve in water and leave the glass behind, and hopefully it won't break when we take it out of the mold. Unfortunately, they are not smooth, so we might need to machine or sand the sample. But the PVA coatings can both sort of make up for that by painting a smooth surface and improve the optical consistency. We can also use our organic glass for proton radiotherapy, range verification for medical purposes. It's one of the most promising treatment modalities for tumors today because in principle, protons can be precisely targeted to deposit their energy into the tumor at the Bragg peak and no further. However, verifying this location can be difficult with some range uncertainties, so we can use a series of OGS bars to image the secondary particles through back projection that escape the patient, such as high energy gamma rays and fast neutrons. We would need to use multiple because our single particle detection systems are unfortunately limited by poor statistics. One of our other group members, Ricardo Lopez, is already working on radioisotope imaging applications. He is working on the HoloLens system for nuclear nonproliferation, which uses OGS bars to image nuclear material for inspection or source location. This also uses back projection to locate neutron and or gamma emitters, and it communicates the information intuitively to the HoloLens AR headset so that inspectors will understand immediately what they're looking at. Just to wrap up, organic glass is a highly promising type of organic scintillator that offers competitive resolution in many ways comparable to that of the leading steel beam material. It makes incorporating additives much easier than it would be for single crystals. Recrystallization and mechanical stability is a concern, but this can be addressed with coatings and other stabilizing compounds. It is useful in a host of applications ranging from medical imaging to non-proliferation, and we are still looking for many more types of organic glasses that can scintillate that have yet to be discovered, along with new and better dopants for the organic glass we have already. Probably the best reference material is Chapter 8 of Springer's Plastic Scintillators, Chemistry and Applications, was written by Patrick Fang at Sandia, all about the organic glass. Thanks, everybody. Does anybody have any questions?
Thank you,
Thank you
Erin,
so
for
much,
your
Aaron. Thanks so much, Aaron. Yeah, we'll just go through some of the questions from the Q&A now. So first question I'm looking at is someone's asking what type of bonds are responsible for bonding when metals are incorporated into OGS? So how are you making sure that the metal is evenly distributed within that material and it doesn't come out of, I guess, the glass as it's solidifying?
That's actually something we're looking to investigate. So the metal atoms, like tin, aren't just free floating. They are chemically bonded into an organic compound. And then because like dissolves like, we're hopeful that that organic compound is dissolved and evenly distributed throughout the organic glass. But we do want to do some optical testing to see how homogeneous it really is.
And since you mentioned optical testing, someone's also wondering how are you maintaining optical transparency and scintillation efficiencies with these high metal concentrations? And yeah, so how are you making sure it's still optically clear and it's not becoming cloudy?
RMD developed the tin compound, and when we melt the glass down and pour it, it seems clear, even though the numerical numbers for light output are a little less. So we're working with RMD to see if we can find alternative formulations that maybe won't have that problem. The exact composition is proprietary, but it does have some alkyl chains which could serve as electron traps. But in
And when you
general, the amorphous nature of the glass helps keep it optically transparent, and mixing in the additives, you know, mixing in the additives, we, that could have different effects on recrystallization. It could make it better. It could make it worse. We're looking at getting some equipment from the chemistry department to see if we can quantify it.
and when you dope these materials, how do you make sure you're maintaining radio purity?
Maintaining what?
Radio purity, making sure you're not introducing like a radioactive source in, like, because everything goes off a little bit of radiation. Or is that
So
not
for
an
more
issue?
rigorous measurements, we would take a background measurement first without any radioactive sources, and then subtract the background count rate from the measurement we take with the sources. So that should account for that.
And then someone else was asking, is there a depletion period of the detector? So like what is your expected effective range of the detector? Like how long do you expect to be able to use the scintillator?
I've been using the same tin-loaded glass cubes in different experiments for a few months. One of them is starting to degrade a bit now, so I'll have to take a second look at it when I go back to the lab and maybe recast. Reapplying the PVA coating periodically may help. We can also look into finding a more permanent sealant that would, sort of stay attached. But with our process as it is now, the cubes can last at least a few months.
And what causes this coating to become or to not last that long?
Hygroscopicity, partly.
Mm.
PVA is water soluble. Some of it might also be rubbed off on the silicone grease with uncoupling and recoupling the cube, as long as the Teflon tape, as well as the Teflon tape.
And then for someone was wondering, can you talk a little bit more about the oven temperature during the glass making process and also remelting process, and how you know which temperatures to choose and how you're adjusting that temperature throughout the process?
I'm sorry, what do you mean which textures to use?
Temperatures, sorry, oven temperature.
We know that our regular organic glass, we can get a good melt at around 215 degrees Celsius. That's just based on a balance of, obviously we have to be at or above the melting point of the glass. We can't let it get too hot for too long, or else it'll start to yellow. But we also need to have it at a high enough temperature, meaning a little bit of wiggle room above the melting point, that we can effectively get the gas bubbles out with the vacuum. In terms of oven temperature, that's a lot of trial and error. Currently, we start it at 130 degrees Celsius and cool it down to room temperature. A lot of our procedures are based on what RMD and Sandia have done.
And then with these glass sand layers, how do they compare, in efficiency, durability, and cost to some of the other scintillators on the market? You know, what's your sell to us?
Well, their performance is almost as good as steel bean, but they're a lot cheaper and easier to grow and make. They can be plasticized with the right hard or soft blending of other compounds. So really, you can get most of the advantages of any scintillator and avoid the downsides.
And are these glass scintillators easy to work with, or are they, the process of synthesizing them be a little finicky for you?
Generally, yes. We order we order the compounds and we just melt down the mixture and pour it into the molds. So we just have to keep the vial melted over the hot plate until it's ready to pour. The main challenge with that is degassing and preventing air bubbles from getting into the mixture. We've had to look at our vacuum system and see about getting a needle that will tighten further onto the cap.
I remember in one of your previous slides, we saw some bubbles within the some of the glass scintillators that were formulated. Um, how does this affect the sensitive volume, such as like light collection and also detection efficiency?
It's bad for it's bad for optical transparency and therefore detection efficiency, because it would have a, first off, it wouldn't be collecting radiation directly because it's just air, but it would also be a point for the scintillation light rays to refract, and then they could potentially escape the detector or not be resolved as clearly.
And so, have you been able to reduce the amount of bubbles within your glass scintillators over your research, or is that
Yes,
still a challenge?
that is an area of progress. We figured out that we can degas the molds first, and then more glass bubbles won't enter while it's cooling.
And how do you account for like micro bubbles, like quantifying the like maybe bubbles that you can't see with your eye?
I wish we could. That's gonna have to be part of that's probably gonna have to be in the same formal optical transparency test as
Mhm.
recrystallization. Right now, we just do our best to get all the macro bubbles out.
Okay. And then you were mentioning when you wrapped your scintillators with tape, you saw improvements or you saw a difference between specular and diffuse reflection. Could you explain a little bit why you see that?
Ah, here it is. So the specular reflector, I suspect, is more efficient. Specular means it's basically like a mirror. It reflects the light in, like, it's a smooth surface, it'll reflect the light in a determined direction, whereas the diffuse reflector can reflect light in many different directions, meaning it's more likely to bounce out or cause other scatters that would have distorted energies.
And also on the topic of energy resolution, um, in the when you're doing your, sorry, I'm just pulling up the question. Looking at the photo or the Compton edge, does Doppler broadening have any effects with the higher Z materials?
Sorry, I'm trying to find the slide. Here, the Compton edge. In terms of Doppler broadening from high Z materials, I wouldn't really expect that to be significant at the scales, at the small distances between the source and the detector, and neither the source nor the detector is moving. So yeah, I doubt that would be significant.
Okay. And how do you characterize or how are you characterizing the optical clarity of your scintillators?
Mostly in terms of light yield. How many photons can we get out per input photons? Because the fewer we're getting, the more light loss that's occurring, and then the less transparency that would mean.
And then for, how do you notice a big difference in transparency when you dope your scintillator with metals to increase your gamma sensitivity? Or is that something, or have you not seen a drastic change in optical clarity?
The tin-loaded glass does have a bit worse light yield. I'm not sure if that's entirely a matter of transparency or of, pure optical transparency versus how much of that is creating electron traps with the alkyl chains.
Mhm. And then for the process of synthesizing the scintillator, you're just saying you get the components, and then how do you know what ratios or the amount of each component you need to put into your scintillator, and what's the process look like for
They
making it?
mix it for us. We're just testing it for them. Once we start experimenting new dopants, then we'll have to use a scale and do it ourselves.
What are some dopants you'll be looking at in the future?
So that's actually a great question. I'm working on my prospectus and I want to start with bismuth pivalate and triphenyl bismuth because bismuth is an even heavier metal than tin, so even higher Z. It's pretty non-toxic, and having the pivalate versus the triphenyl will really allow us to see the effects of those alkyl chains versus aryl groups.
Okay. I think we got through most of the questions. Let me see. Yeah. If there's anything else anyone has that we didn't get through, please feel free to email us. And thank you so much, Erin, for your great talk.
You're welcome.